Okay, we're going to be looking at problem 9, chapter 4, another type of truss that we're going to be resolving through method of joints. So we have external loads here. It says 20 kips acting down, 10 kips acting to the right. We have 5 kips like that. We had 2 reactions. We have a reaction at A, that's a pin. We're going to model that up and to the right. And this is our AH, our AV. This is reaction at B. It's a roller. It's going to react it up. And we have joint C, D, E, B, and A. And this is 10 feet, 10 feet, and this is 5 and 5. So first thing we're going to do is do a reaction sum of forces in X. So in X we have our AH plus 10 is equal to 0. Therefore, our AH, so minus 10 indicates that we indicated that wrong in the beginning. So we're going to correct that when we get into the joints. So we're going to go sum of forces in the Y. We have -5, -20 plus our AV plus our BV is equal to 0. And that gives me our AV plus our BV is equal to 25. Distribution, we'll do a sum of moments about any point is to equal 0. Clockwise moments are positive. We're going to go ahead and take moments at A. Knocks out these guys and that one, so we'll just be left with this through here. So we've got 5 plus 10 is 15. 15 times 20, and that is a plus rotation. This is also tending to turn it clockwise. That is 5, so we have plus 5 times 10. And then we have RBV minus 10 RBV is to equal 0. So what that's going to give us, 15 times 20 plus 5 times 10, that's going to come over as a negative 350 divided by negative 10 gives me a positive 35. So this is acting up in 35. When we plug that in to our AV, 35 comes over as negative 35 plus 25 gives me a negative 10. And that tells me that our AV is acting down. So we had 2 mistakes here, and we're just going to correct those now. And so what we're going to do is replace RBV with what its known value is, 35. And this reaction we're going to fix. We don't want to go into the joints with negative values. So what we want to do is correct all of that. So we're going to get rid of that arrow and that arrow and act it in the correct direction. So this guy is actually going down and this one's going to the left. So this is 10 and this is also 10. So we're now ready to proceed with joints, and we've got to look at where the best place to start is. And again, you want to look at where you got the least going on. Reactions very often are the places to start, but here at this reaction we have too many unknowns, so this wouldn't be a good one. That wouldn't be a good one. So really, it turns out this is a really good one here. So we're going to start out at C and progress through that as we go. Okay, so we're going to start out at joint C, and we're going to bring in all of the information. So we know that we have a 5 kip external load. We have a member here with unknown values and a member here. So as I look at this, it's pretty obvious that this one is going to be up. We're going to call that AC. This one doesn't really matter because, as we'll see, that's going to resolve very nicely, but this is CD. So as we get into this, sum of forces in X must equal 0 by equilibrium. CD doesn't have anything against it, so therefore it's 0. That one was easy. And that'll be nice to feed into the next joint when we get to that point. Y, then we have -5 plus AC has to equal 0. Therefore, AC is equal to 5. Quality of that is compression. And so that one resolves very, very nicely. So we can now go to the next joint. So at this point, when we talked about that before, A was not a very good place to start because it had too many unknowns. But now that we have information for A, we can go ahead and do that at A. So I'm going to do a joint at A, and I'm going to bring in my reactions first. So I have 10 kips and 10 kips. We just solved the AC member to be a compression member. So that'll be compression coming in on this at 5 kips. So then we have an unknown diagonal, and we have another one like this. And the diagonal is AD, and the horizontal member is AB. And if we look at this, we can determine, because this guy has no vertical, this guy has to be the vertical component that's going to cancel. So I'm going to say that's up, because his vertical component will cancel that. And I'm going to go ahead and call this a tension member. So I'm calling them both tension, but we'll see whether that really turns out to be or not. So we're going to start here with sum of forces in the X have to equal 0. In the X we have AB plus AD horizontal minus 10 equal to 0. That gives us AB plus AD horizontal has to equal 10 kips. Okay, so no resolution at that point. So we'll look at sum of forces in Y. And if we don't get it here, then we went on to a joint that won't work. So we'd have to pick up and go to another one. So let's see what we've got. We've got AD vert acting positive, -5, -10. There's your 5 and your 10. Gives me AD vert is equal to a positive 15. So the positive indicates that we do have this going in the right direction. Knowing the vert here, we can solve the horizontal. So we've got a geometric relationship. This happens to be 10 on 10, 10 horizontal, 10 vertical, so it's a 45-degree angle. So that ultimately means that ADV and ADH are equal. But if you just want to prove that, you can say that ADH is to the distance over it operates as 15 is to the distance it operates. And you can see 10 times 15 divided by 10 is 15. So what that means is that ADH is also equal to 15. So that means AB is going to be equal to 10 minus 15, which gives us a -5. So that means AB is not a tension member, it's a compression member. And AD is indeed tension, and that's going to be 15 squared plus 15 squared square root, and that will give us 21, 21, that is in T, tension. And there's our joint A. We can move on to the next one. So at this point, we have quite a lot of information, and we could probably go to pretty much any joint now. We have enough, but I'm going to go ahead and go to joint B and do the free body at B. So we have an external reaction of 35. We have member coming in, that was AB. We determined that to be a compression member. So that's compression. This guy has a force acting this way, and we have a diagonal. So diagonal, again, is always the one that you want to kind of shoot for, look at, because this one, you can usually resolve whether it's compression or tension. So as I look at this guy has a vertical and a horizontal component. That has no horizontal. So this horizontal has to go this way, and if that's the case, that means that this guy will be going like that. And I'm going to just go ahead and model this way. So we're going to call this BE. We'll call this BD. And again, remember, as we said before, if you make the wrong assumption, not a big deal. We just start it when or we just correct it with the sign. So let's go sum forces in X equals 0 first. So in X we have 5 minus BE horizontal is equal to 0. So therefore BE horizontal is equal to 5. And notice that we do get a positive result there, so that does indicate to me that I got that right. So knowing this diagonal and the relationship, we should be able to solve this one in terms of BEV. So let's write the equation first for Y, and then we'll come back and solve what we need. So in the Y, we have BD, which is minus B evert plus 35, and all of that is equal to 0. And so what that essentially gives us is BD plus B evert is equal to 35. And I'm just if you bring those guys over and flip them, you're just getting positives. I just like to get rid of negatives sometimes. So what we need to do is resolve BE vert, and we notice because BE vert is related to BEH, this happens to also be a 45 relationship because it's 5 over and 5 up. So again, like we said before, they're the same, but if you want to prove it, you can just write BE vert is to a distance of 5, as 5 is to a distance of 5. When you do that resolution, you'll notice that BE vert comes out to be 5. So when we plug 5 back into here and bring it over, this gives us 30. And we indicated this as a compression member. The positive says, yep, you guys are right. So there's that. And then we have BE itself, which is equal to 5 squared plus 5 squared square root. And that gives us a value for BE of 7.07, and that's also compression as we indicated it initially. Okay, so we're just about done now. We have one more joint to get to before well, two more actually, I think, before we finalize it. So I have two more joints to do. I can do either D or E. I'm going to go ahead and go up to D. Again, it's just my choice. It's probably got more complex going on there, and so it'll just we'll just do this one first. So what we have is, let's see, nothing external coming in on this. It's all internal members. So we do have this guy coming up like this. We just solved that as a compression member, and that was 30 kips. So we're going to go ahead and put that in. This one we solved initially. It turned out to be a zero force member, so it doesn't have any load on it. If we look at this diagonal, that diagonal was the diagonal from A to D. A to D was a tension member. So this was a tension member. And you're going to need the two tension forces, the horizontal and the vertical. So you have to go back and look through your work and be careful. So this one was a 45 relationship. So these turned out to be 15 and 15, and that's real nice when you have that. Okay, so we've got one more unknown here, which is this guy coming in like this. So again, we want to look at this and see what's out of balance. And it looks like this is going this way, nothing resists it, so this has to go this way, so that means this guy has to be down. Okay, so we're going to go ahead and call this DE. And we're going to do sum of forces in the X have to equal 0. So in the X we have DE horizontal minus 15 equal to 0. DE horizontal therefore is 15. And so it's positive, so that does indicate that we've got this going the right way. Now, when we do the vertical, if the vertical comes out to be negative, we've got a problem. You can't have one positive and one negative. They either have to both be positive or both be negative when you have a diagonal. Okay, so let's go with the y's, and we have 30 up minus 15. And that covers that. And then we've got minus DE vert has to equal 0. So 30 minus 15 is 15, comes over as a negative 15, negative on both sides, means the same thing as positive on both sides. So this is what we need to see here. So they're both positive, and this is a 45, so this is 5 on 5. They have to be the same. If they were different sign or different values, we'd have a problem, which we're good. So the actual value for DE is 15 squared plus 15 squared. Take the square root of that, and that gets us 21, and that is a tension member based on what we indicated. And so there's that one. So one more to do, and this should resolve to 0. So now we're going to do a joint E. This is our last joint. If everything should go to 0 at this point, if it doesn't, we've got a problem. Okay, so we have to bring in everything that we know. Now we have two external loads. I like to do my externals first just because I don't want to forget them ever. So we have two external loads, 10 kip acting this way and a 20 kip acting this way. So we just resolved this guy, and he was a tension member. So he's doing this and this with the two components, and I believe that turned out to be 15 and 15. We had another diagonal coming in like this initially, and that was the diagonal BE, and that was a compression member. So that's compression, and that was a 5 this way and 5 this way. So when we resolve this, everything should go to 0, and if it doesn't, again, we've got a problem. So in the X, we have minus 15 plus 10 plus 5. And when we sum that, it should equal 0, and it does. That checks. Sum of forces in the Y has to equal 0. In the y, we have 15 up plus 5 up minus 20 equals 0. So 20 minus 20 is 0. This is good. So if this doesn't happen here, then the first place, as I've said multiple times, is that you need to go back, look at your reactions, check your reactions first. If the reactions check, then it has to be something within your free bodies somewhere. And once you get through with that, then it usually works pretty well.